Today's lesson has to do with simplifying rational expressions. And before we do so, there's one very crucial theorem that we need to rely on. So let's see if we can't go through that theorem and actually the proof of it. And for every A and B and C belonging to the set of real numbers where B is not 0 and C is not 0, A times, or let's call it C, divided by B times C, what do you think you would like to say that this is equal to, Steve?
A over B.
This then is equal to A over B. And in fact, for emphasis, let's also write, and A over B then is going to be equal to AC divided by BC, and we can come to this conclusion almost immediately from the first statement. Is that right? And let's actually run through the proof of this, in which here then will be our statement, and the reason for that statement. And I think you'll agree that it's quite a straightforward proof. Let's look at the left-hand side, in which we have A times C. This is a C divided by B times C. And there was one very important theorem that came out right at the beginning of this chapter that had to do with A over B times C over C. And if you remember this had to do with what? Does anyone happen to remember the name of this? Oh, the name that we gave it, I believe, had to do with product of quotients. So let's just call it that, all right? And the names are not too important, but simply to realize that, in fact, this is one of our statements that we have already proven. And now this then is going to be equal to, and I think we can perhaps skip a step in here in which we can say that C over C is equal to 1, and our reason that we could give for this probably would be what? Can anyone think of any reason here? This is really C times 1 over C, and C times 1 over C is equal to 1 from our what? Well, probably, Michael, our multiplicative inverse axiom. I think we can include that as our reason, the multiplicative inverse axiom. And of course, we have here then that this is equal to A over B, and this is our multiplicative axiom of the number 1. Is that right? Okay? And immediately then, let's call this step 2 and step 3. Therefore, let's now use a property which says that A over B then is going to be equal to, and we have A times C over B times C, and our reason for saying this is what? Starting from this side, if x is equal to y, then y is equal to x, and does anyone remember that property that had to do with equality, Doug?
That's symmetric.
That's our symmetric property or axiom with respect to equality, okay? And now this theorem, this original statement that we have here, actually in most of what we're going to be doing today, we're going to be relying on the left part of the theorem, that is, if A times C divided by B times C, or rather AC over BC, then is going to be equal to A over B. As we go along in this chapter, you're going to see that indeed we're also going to need the right-hand part of this statement as we go through some of our problems. Again, the purpose of this is to simplify rational expressions. So let's look at a number of examples of these and see how it might go. And let's just pick out a rather straightforward example, such as 6ab squared divided by 3a squared b. And without going through every possible step, relying on the theorem, I think you can look at this and say, oh yes, 6 over 3 has another name for 2, and we certainly are relying on the theorem because 6 is 2 times 3, and 3 over 3 is the number 1, and that's certainly the theorem that we have just proven. And now let's see, what else may we have in the numerator? And here we have b squared divided by b may be written as what?
B
times b, and in the denominator we will have then simply a. Now notice we have here an expression on the right-hand side, which is what we might call a simplified expression from the left-hand side. Or else we may also use the phrase that we have reduced this expression to the lowest terms. We have also used that word and that phrase to describe what's going on here. Now notice it is in lowest terms, or it is the most simple name, when there is no common factor in both the numerator and the denominator. Is that right? And that was the agreement that we have made. Of course, also, A cannot be 0 and B cannot be 0 in order to make this statement true. Well, let's look at a few more examples, perhaps some that are a bit more complicated. Oh, let's look at 3x squared y minus 6xy squared times, and now let's throw in an idea that we had from one of our earlier lessons, times this number raised to the negative 1 power, okay? And now let's then rewrite this in a simplified form in which we may have here a numerator and then times 1 over this expression, is that right? And this number times 1 over that number then may be thought in terms of this numerator and what then this is going to be in the denominator, but what? X minus 2y, and now we may simply, well, let's look at the numerator and ask ourselves if there's some number which we may factor from there, and the greatest common factor here is
3xy.
there's a 3xy times, and whatever is left is
X minus 2.
x minus 2y, and lo and behold, the problem is rigged, because in the denominator it's also an x minus 2y. Now notice what I would like to do here, in which, let me put a mark through these two to indicate that in fact there is a name for the number 1. This is simply a bookkeeping arrangement, so to speak, in order to help us keep track of what our result is. So then this finally then is going to be equal to what? 3xy. Now notice here that we have x minus 2y divided by x minus 2y is another name for the number 1 directly from our theorem. And the fact that you cancel these out, so to speak, please do not think of that as being 0, as some people do. It's a very common mistake. Now, of course, x cannot be equal to 2y here in order to have this expression to be a meaningful one, and in order to be able to have our original statement equal to 3xy. By the way, from now on, let's make the agreement that for all values of the variable for which the denominator is 0 are automatically excluded from our domain of numbers, okay? And that way we won't have to say it every time. Well, let's look at a few more examples. Suppose we had a squared plus ab divided by b squared minus a squared. And there's a little bit of a twist in this problem, and let's see what it looks like. And let's see now, this then is going to be equal to, and you say, well, in my numerator there, we may factor, what, Doug? A times
A plus B.
times an a plus b. Now looking at our denominator, we see that this will factor into b minus a times b plus a. Perhaps some people would rather look at that and think of it as the opposite of something. And what then would be the opposite? What would we like to put inside of our parentheses here? But, Peter?
The opposite of a squared minus b.
This is simply a squared minus b squared. Now perhaps in this problem it doesn't make too much difference as to how we write it, but let's include it in this case right here. Now in the numerator we still have a times a plus b, and now in the denominator, if we thought of this as the opposite of, and we may then factor that into what? And here we have our pattern of what?
A minus b.
A minus b
Times a plus b.
times an a plus b, and right here now you see a name for the number 1. Now notice we're not putting in every step from our theorem, but I would rather that you thought of this and try to get to your final result as quickly and as accurately as you know how. And then you have a over the opposite of a minus b. Now certainly this is an acceptable result, which we may have, but now is there anyone who would rather give us another name for this? And looking at our numerator, there isn't much you can do with that. But the opposite of a minus b, you may write, Doug, as
B minus a.
as simply b minus a. And I think this would probably be the most simple name for the original expression. Okay? Again, it is simplified when there are no common factors to both the numerator and the denominator. Well, let's look at another example. And let's see what we have. Suppose we happen to have some trinomial such as x squared minus xy minus 6y squared divided by some binomial, perhaps the difference of squares. And let's look at this and see what we may say. Let me come down here to the next line. And looking at the numerator, you say to yourself, well, I hope I can factor that. And what might it factor into? Brenda? Let's put an x here times an x here, which is x squared.
It would be
Minus 3 times y.
plus 2 times
And a plus 2y then is going to give us a negative 6y squared, and there's a negative 3xy, plus a 2xy is a negative xy, and sure enough, I think that this is a factor. Everyone agree with that? And now let's look then at our denominator, in which we have x squared minus 4y squared, and Bill, what do you think about that?
X minus 2y and x plus 2y.
X minus 2y times an x plus 2y then will factor. And now looking at this, again you say that the problem has been rigged, because right there is a name for the number 1, and finally then our result is going to be equal to Malcolm,
X minus 3y.
x minus 3y
Over x minus 2y.
all over x minus 2y, and that then is the most simple name. Does anyone want to go for x's here, by the way? Is there another name for the number 1 with these x's? X over x is 1 certainly, and why not? Why not? Because the theorem that we originally proved here has to do with multiplication. It has to do with factors. A times c over b times c is equal to a over b. And here we do not have factors as such. Okay? Well, let's look at another example. And I think that's probably all that we need to do for today. Let's look at something such as 4a cubed minus a divided by 8a to the 4th minus a. And see what we can say about this example. Well, looking at the numerator, what can we factor out of that? And Don?
And
We can take out an a, and whatever is left is what?
4a squared minus
4a squared minus 1, and again you recognize that as a difference of squares. And now looking at the denominator, what can we take out of this? Someone else hasn't said anything? Tim?
1.
A
Times 8a cubed
8a cubed
minus 1.
minus 1. And right there you say to yourself, there's a name for the number 1, a over a is 1. Everyone agree it's in the form of products? Now looking at the numerator, it will factor into what? There again is a difference of squares. Rick?
2a plus 1.
There's a 2a plus 1
2a minus
times a 2a minus 1. And now looking at the denominator, we have 8a cubed minus 1, and there's a pattern. I purposely selected this example because there's a pattern of the difference of cubes. Rick?
2a minus 1.
2a minus 1
Times 4a squared
4a squared
plus 2a
plus a 2a
plus 1.
plus 1. Everyone agree with that? All right, and that indeed is the pattern that we want. And lo and behold, there is a name for the number 1. So finally our result is going to be equal to, and Glenn,
2a plus 1
2a plus 1
all over 4a squared
4a squared
plus 2a
plus 2a plus 1, and that then would be the most simple name for this original expression. Well, let me give you your homework assignment. I think that's all that we need to do for today. This will be